This is the final video on section 1.4, non-periodic waveforms, and we just have one remaining waveform type to discuss. And this is one that you've used a lot in circuits and in your calculus classes, the exponential. So basic exponential would be x of t is e to the minus t. And we're going to add something to that in a second, but let's start sketching it. So e to the minus t would look like this, and it would go off toward infinity, having a value of 1 at 0. Now, we don't like often to deal with infinite signals, so what we want to do very often is we want to talk about an exponential decaying starting at some point in time. So if I want to start at 0 and get rid of what's going on here, I would want to multiply this by 0, but I want to keep what happens after time 1. So I want to multiply that by 1. So now if I multiply the original yellow function by the red function I drew, I get just the decaying section starting at 0. So very often we do that. And that red step I just drew is the unit step, and that will give me an exponential decay starting at 0 and decaying along the axis, but being 0 for all negative time. So what is the value at 0? It's undefined in one sense, because if we go back to calculus, the limit from the left is 0. The limit from the right is 1. So there is a discontinuity in value, or a 0th order discontinuity there in the function. So what does that mean? If I take the derivative, I will have a delta function here. So that's one of the things that happens. If I take the derivative as a step, I get a delta, and we can use the properties from last time to evaluate that. So two more things that we're going to do with our model of the exponential. To generalize it a bit, we can do a time delay. So I could replace all the t's with t minus capital T. So I can take this t, that would be right here inside these parentheses, and I replace that with t minus capital T. And I do the same for the unit step. And now I have delayed it by capital T seconds. So it's still, in this case, is going to start at 1, but it's going to decay from there with a time constant of 1 second. So final thing that we want to do is we want to talk about being able to change the decay rate of the complex exponential. So what we do there is we take the original, but we add a time constant tau in the exponent. So here I have the exponent in the factored form. I still have the unit step. And now for my z of t, I have any time constant I want. So here, let's have capital T, and this is going to start at a value of 1, and I could have very fast time constant, I could have very slow time constant, and that is the exponential. So starting with the basic exponential, we said, well, we want to deal with the time-limited version almost always in analyzing real signals, because we don't want the end where it goes off to infinity, but we do have an event that may happen in a circuit that starts at a certain voltage and then decays, and we can time shift that, And notice you're always replacing t itself with t minus the time delay value. So I have to be careful that the negative is what you apply to the time variable. So I have negative of t minus t, which can also be written this way, negative small t plus capital T. One way to quickly check what's going on in this function is, what if we let the time variable here be the value capital T? Is this working out correctly? Well, if small t right here is equal to capital T, then I see I have e to the 0 power because I have negative capital T plus capital T. So yes, that is where I have e to the 0 and I start with 1 volt. If you wanted to start 5 volts, of course, just multiply the whole expression by a constant 5 and we can scale it up vertically. So those are the things we usually want to do with an exponential as a building block for a signal in a signal system.